Welcome back. We will go ahead with the weld joint and mechanical aspects. Weld mechanics more specifically. We have discussed about other variants like fillet joint, circular fillet joint subjected to torsion, bending moment, and we also have spoken about double parallel fillet joint. So now we will take an example of eccentrically loaded fillet joint. So here you can see, so this is basically the eccentric load which is applied in this cantilever beam. So where you can see that so this is basically a side view of the double fillet joint. Basically this is a case of T joint, and so here the load is acting at a distance from the fixed axis at a distance e, small e, and the length of the joint, weld joint, is L, and throat thickness or joint thickness can be defined as T. So here you can see this is basically the throat thickness. And so here in case 1, so this is the case of case 1. So the T joint fixed at one end and subjected to an eccentric load P at a distance E. So here S is the size of the weld, L is the length of the weld, T is the throat thickness. So here the joint will be subjected to the following two type of stresses, that is, number 1 will be the direct shear stress due to the shear force P acting at the welds, and there will be a bending stress as well due to the bending moment P cross E. That means force cross the distance from its the axis or of origin. So then we know that the area at the throat A is equal to T cross L. Here, because we are talking about double fillet weld, so it is 3 cross L cross 2. This is what is shown here, and then from the previous class, as we know that from here also you can understand that because this is a right angle, so here both these angles are 45 degrees. So here basically the thickness T is equal to nothing but, because this is S, is equal to S sine 45 degree. So that means it is equal to 0.707 into S, size of the weld. So that is what is so here putting the value of T 0.707 S. So then we get that 1.414 S into L. That is basically the area. And so then shear stress in the weld, assuming uniformly distributed, tau is equal to P by A. So then shear stress is equal to P by 1.414 S into L. L is the length of the weld. Okay. Section modulus of the weld through the throat is Z is equal to, as we have shown it earlier also in the earlier class. So here we are calculating again the section modulus, that is T L square by 6, because we are talking about both sided fillet weld. So that's why it has to be multiplied with 2. So it becomes as T L square by 3. Okay, and then if you put the value of T, that is 0.707 S, it becomes by 3. So then finally it assumes the value of S L square divided by 4.242. So this is the value of the section modulus Z. That is what evaluated here, and we know the bending moment as P cross E, force cross distance. So then and bending stress will be sigma B, that is equal to the bending moment divided by the section modulus, that is Z. So M is equal to P cross E, and divided by so here from here we can write P cross E divided by this value, that is S L square divided by 4.242. So then it becomes finally as 4.242 into P into E divided by S L square. Okay, so this is the bending stress value. So then we have evaluated the shear stress, we have evaluated the bending stress. Now we have to evaluate the maximum normal stress. So then based on the formula, that is sigma T max is equal to sigma B by 2 plus root over sigma B square by plus 40 square tau square by 2, as we have individually evaluated the value of sigma B, that is the bending stress, maximum allowable bending stress, and the shear stress. So then from substituting the value of shear stress and the bending stress, from here we can calculate the maximum normal stress, and from based on this formula, and maximum shear stress as well based on this formula, because we know the individual values of sigma b and tau. Okay. So then we are taking another example which is little more complicated for eccentrically loaded weld joints. So in this case, when a weld joint is loaded eccentrically as shown in this schematic, the following two types of stresses are induced. One is direct or primary shear stress, and another is shear stress due to the turning moment. Okay. So here let P is the, so here this P, this force is acting. Let me sorry. Yeah, so this force, this force P is acting over here, and so it is with this eccentricity from the center of gravity, that is G, which is marked over here. So this is center of gravity, and from center of gravity the distance of the load applied is E. So so then and also the length of the weld is L, that is equal on both the sides. It's again, this is a case of double fillet weld, double sided fillet weld, and S is the leg size of the weld, and T is the throat thickness. So then, so now for calculation purpose, let us consider two loads, that is P1 and P2, both equal in magnitude with the applied load P, are introduced at the center of gravity G. Again going back to this schematic. So this is how they are equal and opposite direction they are acting, that is P1 and P2, to balance the load, that applied load P, that is being applied at a distance small e. So then is to produce direct shear stress, which is assumed to be uniform over the entire weld length, and the effect of load P2 is equal to P is to produce a turning moment of magnitude P cross E, which tends to rotate the joint about the center of gravity G of the weld system. So due to the turning moment, secondary shear stress is induced. So here there are two shear stresses. One is the primary shear stress as mentioned over here, direct or primary shear stress, and another shear stress that is defined here as tau 2, that is originated from the turning moment. So for the primary shear stress, that is load by the throat area, that is P by A. A is nothing but T cross L, that is throat thickness into length of the weld, but because we are talking about double fillet weld, so that is why we have to multiply it by 2 with 2. So then it becomes P by 2 T L, and as we know that T is equal to 0.707 into the throat size, leg size of the weld S. So finally the expression for tau 1, that is the direct or primary shear stress, becomes like this. And throat area for single fillet weld, so this is what we have told already. And then since the shear stress produced due to turning moment, that is T is equal to P cross E at any section is proportional to its radial distance from G. Therefore, stress due to P cross E, that is the turning moment at the point A. Again going back to this schematic. So we are talking about now this point A over the joint, that is the edge of the joint, edge of the upper weld. So is proportional to AG, that is AG is equal to R2, that is the radial distance from the center of gravity of the weld joint, and is in a direction at right angles to AG. In other words, so here tau 2 by R2 is equal to tau by R is equal to constant. So that means tau is equal to tau 2 into R by R2. So that is what is shown here. So tau 2 is the secondary shear stress that is generated due to the turning moment at a distance R2, and tau is the shear stress, that is the primary, that is the shear stress that is originated at a distance R, at any distance R. Okay. So then going ahead, so considering a small section of the weld having area dA at a distance R from G. So R is any radial distance from the center of gravity G. So again so you can see, so R is any distance from the center of gravity G. So dA is a infinitesimal area over the weld joint, that is defined as dA. So then so shear force on this small section is as we know that stress is equal to load by area. So load is equal to stress into area. So, it is tau into dA, and turning moment of the shear force about G is dt is equal to the force into the distance. So, this is tau dA into the at any given distance, so that is small r. So, then as we know, as we have calculated here, that tau is equal to tau 2 by r2 into r. So, putting the value of tau over here, that is tau 2 by r2 into r. So, the expression becomes tau 2 by r2 into dA into r square. So, then total turning moment over the whole area we can get by integrating this expression. So, then it is integration of tau 2 by r2 into dA into r square. So, which further reduces to tau 2 by r2 integration dA r square. So, here integration dA r square is nothing but the polar moment of inertia, that is J. So, then I mean, this is also consistent with the formula that we have discussed earlier. So, it is tau 2 by r2 into J. So, that means T by J is equal to tau 2 by r2. So, this is the universally proven law, that is we know, we have discussed earlier also. So, this is the applied torque divided by the polar moment of inertia is equal to the shear stress by the radial distance. So, the shear stress due to the turning moment, that is secondary shear stress, is nothing but tau 2 is equal to T cross r2 by J, T cross r2. So, here please correct it, it should be, there should be a divide sign. So, then it will be, I mean, has to be like, so T is equal to, as we know, that P into E into, so P into E, that is the turning moment, that is the applied load into the distance of the eccentricity, that is P cross E cross r2 divided by J, the polar moment of inertia. So, in order to find the resultant stress, the primary and secondary shear stresses are combined vectorically. So, then the resultant shear stress at point A, that is at the edge of the I mean top weld, that means at point A. So, then combining primary and shear stress secondary shear stress vectorically, we arrive at the expression for the shear stress, resultant shear stress at point A, that is tau A square is equal to tau 1 square plus tau 2 square plus 2 tau 1 tau 2 cos theta. So, theta is the angle between the primary and secondary shear stresses, that is tau 1 and tau 2, and cos theta is nothing but r1 by r2. So, here I mean the polar moment of inertia of the throat area A about the center of gravity G is obtained by the parallel axis theorem. This is for your understanding, where J is equal to 2 into Ixx plus Ax square. So, from here simplifying it, we arrive at this expression, that is 2a L square by 12 plus x square, where x is the perpendicular distance between two parallel axes, L is the length of the weld, and T is the throat area, that is 3 cos L, that is 0.707 into leg size of the weld S into L. So, from this example we can understand that how we can calculate the resultant shear stress at any given point in case of a eccentrically loaded double parallel fillet weld. So, where I mean there are primary shear stress and also secondary shear stress originated from the turning moment. So, with this we have discussed about some possible configurations of the weld joint and their associated mechanics, and also this table shows I mean for your ease it is shown over here, that for some typical geometries, regular geometries, these you can find the expressions written for calculating the polar moment of inertia and also the section modulus, that is often. So, section modulus, as we have learned, that it is needed when the joint is subjected to bending moment, and polar moment of inertia is needed when the joint is subjected to the torque. So, for the individual occasions we need to use the individual formulas to calculate the I mean section modulus and also so I mean the polar moment of inertia. So, I mean so this is the formulas given over here, and now we will move into the I mean different welding techniques. Like earlier we have classified them based on the heat source, based on the I mean power input, based on the I mean whether I mean the I mean externally filler metal addition is done or not. So, now we will try to go about I mean discuss them individually and try to go into the more detail of it. So, we will start with gas welding. So, gas welding is one of the primitive and one of the early welding technique. You might have also seen the gas welding, I mean in even for welding purposes in your household applications, where sound weld is obtained by selecting proper size of the flame, filler material and method of moving torch. So, the temperature generated in case of gas welding is in the order of 3000 degree centigrade, and the metal is, when the metal is fused, oxygen from the atmosphere and the torch combines with molten metal and forms oxides, results in defective welds. Fluxes are added to the welded metal to remove oxides. Common fluxes used are made of sodium or potassium or lithium and borax. So, flux can be applied in case of gas welding as paste or powder, liquid, solid coating or gas, or in the form of gas. So, this is the, I mean, arrangement shown over here. So, you can see this is the nozzle from where the gas is coming out. So, which is connected with the welding torch, and this is the welding flame which is generated, and this is the workpiece where actually the welding is happening, and this is the oxygen house pipe. So, because we are generating the flame by using two different gases, one is fuel gas, that is the acetylene, that is C2H2, okay, and another is oxygen. So, I mean, combining both, we are basically generating the flame and we are accomplishing the welding. So, gas welding equipments, so gas welding generally typical pressure of oxygen are considered in the cylinder pressure of 125 kg per semi square, and in case of acetylene it is considered at 16 kg per semi square. So, different kind of regulators are also used for two different gases, and also we use pressure gauges, hoses, welding torch, check valve, etc. So, I mean, based on the, I mean, content of the individual gases, that means whether it is a rich mixture, whether it is a lean mixture, whether it is a, I mean, 1:1 mixture. So, depending upon that, the, I mean, the shape, also the color of the flame, and also the temperature generated by the flame, that gets changed in case of gas welding. So, I mean, in this case the flames generated are used to heat metals or thermocouples, allowing them to cool. So, most gas welding processes are oxyfuel, uses oxyfuel welding technique. So, it is one of the oldest welding processes. So, here with oxyfuel welding, which is also known as oxyacetylene welding, need a liquid fuel or gas such as acetylene, and the gas is combined with oxygen to raise the temperature of the flame. Okay. So, here the, as I told you, that the flame generated, it can have different temperature and also have different colors based on the different mixture ratio between the fuel gas, that is acetylene, and the oxygen. So, the inner cones are in the flame generated, the inner cores are the hottest part of the flame. This is where oxygen and acetylene combines, and the outer cone is colder because it receives more oxygen from the atmosphere and the surrounding air. So, it is also commonly called the outer envelope or sheath. So, this is the two important segments of the, I mean, arc generated. So, this is, if it is a typical arc, so there is the inner core or cone. So, this is the inner core and this is the sheath or outer cone. Okay. So, this is how basically, I mean, so both these inner cone and the outer cone generally have different colors and also different temperatures. So, depending upon the particular application, we also we can decide that where we need to I mean, the inner cone plays the role of fusion welding, and where the outer cone plays the role of fusion welding, depending upon the heat input requirement. And even in case of, I mean, in particular welding, based on the location of the weld joint and the temperature requirement, and also the stages of stage of the weld joint preparation, we can selectively use the inner and outer cone. I mean, we can selectively subject the inner and outer cone of the flame to the joint. So, I mean, so as I told you, so there are three kind of joints. So, then this is the first case is the neutral flame, I mean, neutral flame oxyacetylene welding. So, in this case, the, I mean, mixture is almost 1:1, I mean, for both the fuel gas that is acetylene and oxygen. So, you can see that there is a inner cone which is a white in color, and the temperature is around 3100 degrees centigrade, whereas the outer cone which is blue in color, bluish, and its temperature is much cooler, which is 1275 degrees centigrade. And this flame is suitable for welding materials like mild steel, stainless steel, aluminium, copper and cast iron. So, it is the flame which is generally used in general purpose welding tasks due to its clean operation. And the second category is basically the oxidizing flame. So, here oxidizing flame, you are seeing that the temperature is much higher, even higher than the neutral flame. Why it is so? Because this is because of the higher oxygen content, higher oversupply of oxygen. So, it is best suited for non-ferrous metals like brass and bronze. It is also used in cutting operations, rather than welding. So, in that case we call it as gas cutting operation. So, in this case the inner cone is same in white in color like the neutral flame. However, the outer color is completely blue. And then the third variant is carburizing flame, which is generally only used for carburizing purpose, because it has a tendency, because it is a kind of flame where the fuel gas is richer. So, we are talking about rich mixture of fuel and the oxygen. So, here so fuel content is more, oxygen content is lesser, and accordingly the temperature you can see it is lesser. So, it is on inner cone temperature is around 2900 degrees centigrade, and there is a difference, is there is a intermediate red zone in case of. So, seeing that you can recognize that your fuel gas content is higher in the mixture, and accordingly you can adjust, one can adjust the regulators to arrive back at the neutral or the oxidizing flame as required. And also it can be utilized based on the purpose, like in case of carburizing, purposefully this carburizing flame is needed when case hardening is involved or surface hardening is intended, because this flame which is rich with fuel gas, that is acetylene C2H2, has a tendency to react with the top surface of the metal, and it also forms metal carbides MC. So, metal carbides creates facilitates hardening, surface hardening of the metal piece. Okay. So, the advantages of gas welding are it deals with simple equipments and simple, portable and inexpensive equipment, and also maintenance and repair costs are not so high, it is quite easy. And disadvantages, of course, that because it is a primitive welding technique, as I told, so it is not good from sustainability point of view, because it deals with the hazardous fuel gases. And also it is it creates large heat affected zone in the weld joint which is getting produced. It causes severe distortion, and not recommended at all for reactive metals such as titanium, zirconium, magnesium, etc. And it also has got very low welding speed and limited power density. So, the next in the line is the arc welding. Yes, of course, it is one of the most versatile welding technique. So, I have already discussed with you in one of the earlier classes about the basic principles, that how we generate arc, that is because of the boiling of the bridges, and that is because of the release of the electrons from the negative electrode to, and which is transported towards the positive electrode, that means the anode, that means the workpiece, and thereby the arc is generated. So, based on the usage of consumable or non-consumable electrode, the arc welding can be classified into and it can be named as TIG, MIG welding. So, it is an example of TIG welding is a example of where the filler metal is not used. So, it is a typical example of autogenous welding. So, TIG is a autogenous welding where we are basically subjecting the workpiece to fuse and joint preparation, whereas in case of metal inert gas molding we are basically consuming the electrode as a filler material in case of joint preparation, and yeah, so that is the difference, but otherwise their working principle is same. The only difference is that in case of TIG, if it is not autogenous, then we have to subject we have to provide the filler material separately, that means it is not clubbed with the welding torch. Whereas in case of metal inert gas welding, it is the electrode which is a consumable in nature, which gets deposited for joint preparation and that is fed through the torch. So, so here, but both these welding techniques use electric arc to polish metals, and arc welding is the most common method of welding metals, and electricity travels from electrode to base metal to ground, and more importantly it is much more sustainable than the previous variant that we discussed, that is gas welding, because it is using electricity and there is no hazardous gases involved. But of course there are some shielding protection gases that we use, but generally they are inert gases and not fuel gases, which can cause severe environmental hazards. So, so these are basically the arc welding equipment that you can see in this schematic, which are marked. So, which includes electrode holder, electrode, wire brush, gloves, goggles, etc. So, I mean, so the power source. So, regarding power source, please recall that in one of the earlier classes we have discussed about considering the drooping current, drooping curves between current voltage characteristics. So that is a very much widely accepted current voltage characteristics that is considered in case of arc welding. Why so? Because any change in the arc length, because of the operator, because of the welding conditions, there should not be much change in the current. There can be voltage fluctuations also in the workplace, but that should not alter the current significantly. So that's why we use the drooping voltage characteristics. So that is what is shown here for both. Because arc welding power source can be direct current based and also can be alternating current based. So for both the cases, the current voltage characteristics should be drooping in nature. Okay. So, so the maximum rated open circuit voltage, which is the voltage between the output terminals when no welding is being done, is normally fixed at about 80 volts. So, this is the maximum, and normally a voltage of the order of 40 to 50 volt should be enough for starting an arc. So, whereas for continuous welding 20 to 30 volt is sufficient. So, the minimum welding load voltage Vm can be calculated based on this empirically drawn mathematical expression. So, then where the minimum welding load voltage Vm is equal to 20 plus 0.04 into I is the load current in amperes. Okay. So, the power source, so the duty cycle as defined by American Welding Society is the percentage of time in a 10-minute period that a welding machine can be used at its rated output without overloading. So, most of the welding machines need not have to operate the full time, since a good length of time is spent in setting up, metal chipping, cleaning and inspection. So, normally a 60% duty cycle is suggested. So, the Indian standard specifies 5 minutes as the cycle, and hence for every 5 minutes of welding transformer operation, 3 minutes is for welding and 2 minutes is for no load operation. So, but continuous automatic welding machines may require the welding machine to operate at 100% duty cycle. Sometimes the suggested duty cycle can also be lowered for higher ambient temperatures, insufficient cooling air quality and low line voltage. So, the actual duty cycle can be calculated as follows, where TA is the required duty cycle, T is the rated duty cycle, and I is the capital I is the rated current at the rated duty cycle, and I subscript A is the maximum current at the rated duty cycle. So, thereby we can basically, if we know this parameter, we can calculate the required duty cycle. So, this is some attributes from the practical industrial usage point of view. So, moving ahead, we will we have already discussed about the electrode, which is basically responsible for arc generation in case of arc welding processes, and it can be of two types, like consumable and non-consumable. So, the example of non-consumable electrode is the tungsten electrode that we use in case of TIG welding, Okay, and consumable electrode can be based on, I mean, several, like, I mean, iron based and all, and also it can be aluminum based, based on the appropriate, I mean, appropriate application in on demand. So that's a non-consumable electrode. The benefit is it is not consumed during welding, and there is a greater control on the generated arc. So that's why, so in case of non-consumable electrode, so they also gets faces depletion over periodic welding processes because of the vaporization. Even though they do not get experience melting and deposition in the weld joint, but because of vaporization there is a loss of the electrode material over a period of long time, and any filler material can be supplied in this case by a separate wire fed separate wire weld pool separate wire feeding mechanism, which is fed into the weld pool. Okay. So, this is the case of non-consumable electrodes, and in case of consumable electrodes, welding rods which are of 9 to 18 inches and 3 by 8 inches or less in diameter and must be changed frequently. So, weld wire can be continuously fed from spools with long lengths of wire. Why these long length of wires are fed from spools? To avoid to achieve continuity in the welding, so that there are no defects from due to improper fusion of the weld metal at the weld joint. So that's why it is the filler rod is fed from using a spool having long length of wire, and so but in both the wire rod and wire forms, electrode is consumed by arc and added to the weld joint as filler material in case of consumable electrode. So as I told before, consumable electrode is a based process such as metal inert gas welding MIG, and non-consumable electrode based process example is tungsten inert gas welding. So now we will move to the importance of flux. So flux is a substance that is used to prevent formation of oxides and other contaminants in case of welding. So it dissolves them, and facilitates removal of the oxides and inclusions. It facilitates protective atmosphere for welding. It stabilizes arc, and also it reduces spattering. So the great example of flux and its potential benefits can be understood in case of submerged arc welding. That all we will be discussing next. So so this basically so here are the steps that are followed in case of arc welding. So it is, first is preparing the edges, like I told you many times, that whether it is a, if it is a butt joint, for example, whether it is a V butt joint or U or J shaped groove, so that need to be prepared first. And then so if it is a gas welding, then opening the acetylene valve and igniting the gas at the tip of the torch. And then if it is the arc welding, then proper positioning of the electrodes, and they are touching the electrode with the workpiece first, so that the arc can be generated, and then holding the torch at an appropriate angle, and also checking the filler rod angle of the filler rod with the workpiece, so that it can feed to the weld zone appropriately. And then so likewise, so so these are some of the advantages of the arc welding, like it is one of the most efficient way to join metals, and it is also a lowest cost joining technique. It affords lighter weight through better utilization of materials, and joins all commercial metals, and provides design flexibility. However, the design disadvantages are it is generally manually applied, so therefore high labor cost. It needs high energy and not convenient for disassembly, and defects are hard to detect at joints. So here are some comparison between gas welding and arc welding. So in case of gas welding, as we have learned, that here the heat is produced by the burning of the gas, by gas flame, and in case of arc welding, the heat is produced by the electric arc, and there is a significant difference in the maximum temperature that can be generated Like in case of gas welding, it is approx 3000 degree centigrade, whereas it is beyond 4000 degree centigrade in case of arc welding. And gas welding, separate filler rod is needed, but in case of arc welding, separate filler rod may or may not be needed depending upon the particular welding technique. And so gas welding is suggested for thin materials, and whereas arc welding is useful for plates or parts having medium to high thickness, and gas welded parts do not have much strength, whereas arc welding parts offer significant strength. And filler metal may not be the same parent metal in case of gas welding, whereas in case of arc welding, the filler metal which is used to fill the joint are either of same composition like the parent metal which are experiencing welding, or the filler metal must be an alloy of the parent metal that is experiencing joining. So, brazing and soldering are done using gas welding technique, whereas arc welding, in case of arc welding, brazing soldering cannot be carried out by electric arc, because brazing soldering deals with a very low temperature. We will discuss about them in detail later. So with this, so there are some special welding processes that we will be discussing next. However, that we will be discussing in the next class. So for this class, we are stopping here, and so see you in the next class. Thank you.